So today let us discuss clearly the conditions of a straight line to become a tangent for circle, and also what are various types of other relations involved related to this tangents concept. Today let us discuss in detail. Here already we have discussed in the last class, when a circle is touching a straight line, suppose this straight line is some Lx plus My plus n equals to 0, and the circle is taken in its standard form s equals to 0, that is x square plus y square plus 2gx plus 2fy plus c equals to 0. Now if this circle is touching this straight line, as per the conditions we have discussed earlier, the perpendicular distance from center to the given straight line should be always equals to the radius of the circle, then only it becomes a tangent. That is, perpendicular distance from center minus g comma minus f to this line will be modulus L into minus g plus m into minus f plus n by under root L square plus m square equals to radius of the circle g square plus f square minus c under root. We can also write it as Lg plus mf minus n whole square equals to L square plus m square into g square plus f square minus c. After taking minus common inside and squaring both sides, we can get this relation. Here, instead of using this relation as a standard formula like using a ready-made result, here better we always depend on this condition that the perpendicular distance from center to this given line is always equals to its radius, then it is called a tangent. So this is the clear tangent condition we take in general in solving problems. Now let us see how to find tangent equation to the given circle at a given point on its circumference somewhere. If you take the circle given as s equals to 0, on which there is a point px1 comma y1 is imagined, then to find out the equation of tangent drawn at this point to the circle, here the center is minus g comma minus f. Let us take this point as C. As we know already, tangent drawn at the point of contact is perpendicular to the radius drawn at this point of contact. That's why CP is perpendicular to the given tangent line. So we can find out the slope of this CP as y1 plus f by x1 plus g. Because this is perpendicular line, hence we can write its perpendicular line slope as minus of x1 plus g by y1 plus f. Now we know the point of contact as well as the slope of this line, hence using slope point form we can get the line equation here, which is nothing but tangent equation. Therefore the tangent equation required is y minus y1 equals to the slope minus of x1 plus g by y1 plus f into x minus x1. On simplification, y minus y1 into y1 plus f equals to minus of x minus x1 into x1 plus g. Expanding these terms, y1 plus fy minus y1 square minus fy1 equals to minus xx1 minus gx plus x1 square plus gx1. Transferring all these negative terms to the other side, you are getting xx1 plus y1 plus gx here plus fy equals to right side we get Yes, x1 square plus y1 square plus gx1 plus fy1. And such a lengthy equation to remember always is a typical task. That's why let us see how to simplify it further in notational form. Already we have various ideas of notations developed in previous classes. Now, if you observe this left side equation, here xx1, yy1, these terms are appeared in S1 notation. In S1 notation, we have xx1 plus yy1 plus g of x plus x1 plus f of y plus y1 plus c. To get that one, we require three more additional terms, which are nothing but gx1, fy1, c. That is why adding these terms both the sides, we get left side xx1 plus yy1 plus g of x plus here x1 plus f of y plus y1 plus c equals to right side x1 square plus y1 square plus gx1 already and plus this one 2gx1 2fy1 plus c. Clearly these are nothing but representing left side S1 and right side the notation S11. But we know that if the point is lying on the circumference, S11 is 0. So that's why this will become 0. Now the tangent equation at the point of contact will be S1 equals to 0 will come. So whenever the point of contact on the circle, we know the circle tangent equation can be written in the form of S1 equals to 0. Now let us see some more conditions related to tangents of a circle. We are choosing randomly a point P external to the circle S equals to 0. And easily we can say that from this external point P x1, y1, we can draw two tangents. Suppose touching it A and B. So here PA and PB are called tangents of the circle S equal to 0 drawn from the point x1, y1, P x1, y1. Here PA line segment length is considered as length of the tangent. So this PA or PB, these two can be taken as length of tangent, whereas these lines are tangents to the circle. Now at the points of contact, if we draw the radii, definitely these two are perpendicular to the tangents. Now we join PC. In this diagram, which is related to tangent, we can get many points related to this tangent standard conditions. Now today let us derive all various standard relations we have, which are useful in solving various types of questions. Now for example, in this diagram, suppose we have to find out length of tangent PA or PB, we have to find out. So here in right angle triangle PAC, if we consider this length of this one PA or PB is equals to under root PC square minus this radius, if we are taking it as some r square. By using Pythagoras theorem, we can write that PA or PB equals to under root CP square minus r square. But CP square minus r square is the definition of power which we know already. So that's why we can write this as S11 under root. Therefore, length of the tangent drawn from external point P x1, y1 to the circle S equal to 0 is root S11. This is taken as the first point in this diagram. Now, second point. In this diagram, PACB, a quadrilateral we are finding, which is clearly a cyclic quadrilateral as the opposite angles are supplementary. Therefore, in this cyclic quadrilateral, what is its area? Let us see. The area of cyclic quadrilateral PACB can be taken as, because these two are clearly congruent triangles from RHS axiom, that's why instead of finding cyclic quadrilateral area, we find out any one triangle and we double it here. 2 times triangle PAC area, this equals to 2 into, because this triangle is a right angle triangle, half into, if you are taking PA as the base, then its height will become R. 2 get cancelled, you are getting R into PA, already we have proved as root S11. So, area of cyclic quadrilateral PACB is R into root S11. This is the second important point to be noted in this diagram. Now, coming to the point number 3. Suppose if we take angle APB as theta, let angle APB equals to theta, then each angle will become theta by 2, theta by 2. Now, in this diagram, opposite is R, adjacent is root S11, applying tan theta by 2 equals to opposite R by root S11. From this, theta can be calculated as 2 tan inverse R by root S11. This is a very important other point to be noted in this diagram. Third point, a very useful technique, a formula for solving many type of locus conditions especially. We discuss about all this while doing problems here. Coming to the fourth one. Point number 1 here is length of tangent PA or PB equals to root of S11. Point number 2, the area of cyclic quadrilateral PACB equals to 2 times one of these triangles area, and which is equals to R into root S11 we have calculated. And the third point is angle between tangents drawn from this external point to the circle is 2 tan inverse R root S11. Point number 4. If we join this both points of contact, you are getting a chord which is nothing but called as chord of contact. This is the chord obtained by joining points of contact. So, AB is called particularly here as chord of contact. Now, PAB is the triangle formed by both the tangents and its chord of contact. Now, let us see how to find out this triangle area also. So, the fourth important point which we are going to derive here is the area of triangle APB. The area of triangle PAB equals to, I am using sine formula for finding this area of triangle, half into PA into PB into sine theta, half into root S11 into sine theta, we can use 2 tan theta by 2 by 1 plus tan square theta by 2. If we cancel this 2, you are getting S11 into tan theta by 2 already we have calculated in third point here. Substituting in this, R by root S11 by 1 plus R square by S11. Simplifying this, you are getting R into S11 power 3 by 2 by R square plus S11. This is the fourth important point we are deriving in this. Here, the area of triangle formed by both the tangents and their chord of contact is R into S11 power 3 by 2 by R square plus S11. Now, in the diagram again, if we observe, we are finding one more triangle ABC. The triangle formed by both the radii drawn at A and B and the chord of contact. One can guess comfortably that this triangle area is nothing but total cyclic quadrilateral area PACB minus this PAB area. Easily we can calculate this one. If we are calculating the difference between these two, the result we can easily prove that appears as if almost similar to this, but simply by transferring this power 3 to this R. After calculating the difference between this total area R root S11 and this triangle area, we get the result finally as the result obtained by transferring this power 3 to R, that is the area of triangle ABC equals to R cube into S11 power half by R square plus S11. This is taken as our fifth important point in the diagram. Now, coming to the next point. Now, coming to the sixth point in the same diagram. In this diagram, we are finding different polygons here. PACB is a cyclic quadrilateral. PAC, PBC, ABC and PAB are four triangles we have which are involved with this diagram. For these four triangles and the cyclic quadrilateral PACB, because all these five are cyclic, we can draw a circle passing through all these five vertices, five diagrams vertices. So here we can observe strangely that the circle passing through the vertices of all these five diagrams will be common. Here the circumcircle of PACB, then triangles ABC, PAB, PAC and PBC. If we analyze circumcircle of PACB, cyclic quadrilateral, PAC, PBC, ABC and finally PAB. For all these five figures circumcircle if we want to get, once observing the diagram, because this is a right angle and this is also a right angle, and we know already that the angle in a semicircle is always a right angle. That's why we can consider PAC as angle in semicircle. In that case, we can draw a semicircle with PC as a diameter, and also we can draw one more semicircle on the other side taking PC as diameter. Clearly, we are getting the circumcircle of all these five diagrams will be the circle with PC as a diameter. We know already the center as minus G comma minus F and the given point is x1 comma y1. When these two considered as extremes of a diameter, the required circumcircle of all those five figures can be written as x minus x1 into x plus G plus y minus y1 into y plus F equals to 0. This is considered as the circumcircle of all of these four triangles and one cyclic quadrilateral. This is taken as our sixth point. Now, point number 7. In this diagram, if we join A and B, we are getting the chord which is called the chord of contact. This is called the chord of contact of the point x1 comma y1 with respect to the given circle. Now let us see how to find out this chord of contact equation. If we assume this point A as some x2 comma y2 and if we assume this point as x3 comma y3, then because the point is on the circle and this is a tangent at this point of contact, that's why we can get the tangent AP equation as S2 equals to 0. Already we have derived in the last point that tangent at x1, y1 on the circle is s1 equal to 0. In similar way, tangent at x2, y2 on the circle taken is s2 equals to 0. But this tangent is clearly passing through the point x1 comma y1. So this point will satisfy that line equation. Substituting, you are getting what? S12 equals to 0. S12 or S21, that is our choice. Both are equal. In a very similar way, tangent at x3, y3 is S3 equals to 0. And clearly this line is passing through the point x1 comma y1, and hence it will satisfy that equation. So S13 also you are getting 0. Actually, S1 equation, if we consider, S1 represents always general form of a straight line. Already we know the notational terms of S1, which contains strictly x term, y term and constant terms. That is why S1 represents always a straight line. And now here we have proved that this straight line is passing through the points x2, y2 as well as x3, y3. Because passing through the given 2 points, we can define a unique line, and that's why that unique line equation will be considered as S1 equal to 0. Surprisingly, earlier we have discussed that at x1 comma y1 on the circumference, tangent equation was proved as S1 equal to 0. Now if the point is taken external, same point x1, y1 is taken external, that equation S1 equal to 0 will be turning as its chord of contact. So S1 equal to 0 represents not tangent always. If the point is lying on the circumference, that equation represents tangent. If the same point is lying external, that line has become its chord of contact. Is it clear now? Now coming to the last point in this diagram, we have point number 8. Here, sometimes we can draw tangents to the circle which are perpendicular to each other. If we join all such points, the locus of such points of intersection, locus of a point from which we can draw perpendicular tangents to the circle. For example, if we are able to draw two perpendicular tangents to the circle, then if we join all such points, we are getting its locus as a circle concentric with the given circle, which is called its director circle. So our 8th point is director circle. The locus of a point from which two perpendicular tangents can be drawn to the given circle s equal to 0 is defined as its director circle. How to find out this director circle equation? Now let us see. If we are considering this point as x1 comma y1, now angle, suppose this point is taken again as P, then angle here APB equals to 90 degrees we are getting. But actually the angle already we have proved it. 2 tan inverse R by root S11 is 90 degrees. Implies R by root S11 equals to, we are getting tan of 45 degrees is 1. Squaring and cross multiplying, you are getting S11 equals to R square. Now the locus, if you want, replacing S11 with S, you are getting director circle equation as S equals to R square. So this is considered as the last point of this diagram. Like this, we can derive 8 important points just from this diagram. If we just recapitulate all these 8 points from the beginning here, point number 1 is length of the tangent PA or PB equals to root S11. Second point, the area of cyclic quadrilateral PACB will be r into root S11. Point number 3, angle APB, angle between tangents, we can derive it as 2 tan inverse r by root S11. And fourth one, area of triangle formed by both the tangents and their chord of contact will be r into root S11 by 1 plus r square plus the area of triangle formed by the tangents and their chord of contact is r into S11 power 3 by 2 by r square plus S11. Just if we transfer this power 3 to r, then r cube into S11 power half by r square plus S11 represents the area of triangle formed by both the radii and their chord of contact. Now coming to the sixth point, the circumcircle of PACB, triangle ABC, triangle PAB, and both of these triangles PAC, PBC will be always same, which is nothing but the circle with PC as diameter. This is the circumcircle of all of these figures, which can be taken as x minus x1 into x plus g plus y minus y1 into y plus f equals to 0. And after that, this AB, which is nothing but called as chord of contact of the point P, can be derived as S1 equal to 0. Here the very important point is, if the point x1 y1 lies on the circumference, S1 represents tangent equation. If the point is external, the same S1 equal to 0 can be written as the equation of its chord of contact. And finally, coming about the director circle. Director circle is defined as the locus of a point from which perpendicular tangents can be drawn to the given circle is considered as director circle, and its equation is derived as S equal to r square. Here we can also find out its radius of the director circle as root 2 times the radius of the given circle, and of course it is concentric with the given circle. Therefore, director circle can also be obtained by using center radius form, because the center is same as the given circle center and radius is root 2 times the radius of the given circle. That's why we can use center and radius form also for getting circle equation. But this is the best way of writing director circle equation in simple one step, S equal to r square, without disturbing circle equation. Just in the right side, in the place of 0, replace 0 with what? R square. This is representing circle equation, director circle equation. Now let us see the relative positions of two circles. How to compare the position of a circle with respect to another circle. What are various positions possible here? Let us see. Now here in all these cases, just we imagine two circles with the radii r1 and r2 and centers as some a comma b, and also we imagine that the distance between centers AB as some d for our convenience. Here coming to the first case, suppose the circles are taken like this. Each circle is external to the other. As I told you earlier, centers of these two circles are taken as A and B. Distance between these centers taken as D. This radius is R1, this radius is R2. From the diagram, one can guess very comfortably that distance between centers is greater than sum of these two radii. So whenever we find the condition D greater than R1 plus R2, the given two circles are external to each other. They don't have any common point, as well each circle is external to the other. If they are coming little bit closer to each other, in that case we get the second case. If the given two circles coming closer to each other, then because this is R1, this is R2, which is equals to whose sum is equals to the distance between centers will come here. So whenever we get D equals to R1 plus R2, clearly the given two circles touch each other externally. So they are touching externally in this case. Next case, still if they are coming closer to each other, like this, they cut each other at two distinct points. In that case, distance between centers will be less than the sum of these two, R1 plus R2. And also we can show that this is more than difference of these two radii. If distance between centers lies between the numerical difference and sum of the radii of the given two circles, they cut each other at two distinct points. Fourth case, if they are still coming closer to each other, suppose the given circles are like this. If they are touching each other externally, this is center of the outer circle. Suppose this is center of the inner circle. This total length is outer radius, this length is inner radius. So this D will be outer radius minus inner radius, which is taken as the numerical difference between these two radii. When D equals to numerical difference of the radii, they touch each other internally. Coming to the fifth case, here clearly the second circle is completely inner of the first circle, in which case the distance between centers D is less than even the numerical difference between R1 and R2. Here, whenever D is less than R1 and R2, then in this case, here one circle lies completely inside the other. And coming to the sixth case, in this case, both the centers A and B are coinciding and R1 is not equals to R2. If R1 not equals to R2 and centers are coinciding, in that case D will be 0. Then distance between centers is 0 but the radii are different, then clearly the given two circles are called concentric circles. Apart from all these 6 cases, we can also see one special case, seventh one, that is D equals to 0 and R1, R2 also same. Here AB both are coinciding, hence we get D equals to 0. Even the radii also same, in that case we are getting both the circles coinciding each other. So here instead of getting two different circles, both the circles are representing same circle in xy plane. So these can be taken as coinciding circles. Like this, we have 7 relative positions in the xy plane for any two circles given. Clearly we can locate the relative positions with the comparison of D and R1, R2 various cases. If you recapitulate all these cases in order, if the distance between centers is more than R1 plus R2, they are each one external to the other. If D equals to R1 plus R2, they touch each other externally. If D lies between numerical difference and the sum of the radii, then they cut each other at two distinct points. Fourth one, D equals to the numerical difference of radii, they touch each other internally. If D less than R1 minus R2, then one circle lies completely inside of the other. In this case, if you go little forward here, if AB distance between centers has become 0, means centers are coinciding, it becomes concentric. Clearly R1 not equal to R2. In concentric circles, if R1 equals to R2, we are getting the two circles will be coinciding like the seventh case. So exactly there are 7 relative positions in a plane for the given two circles. If one understands clearly how to find the relative positions of given two circles, now in these 7 relative cases, we can check one more important fact also, that is about common tangents. How many common tangents we can draw in each case also we can see. If you observe these common tangents are two types. If you observe the diagram of this first case, here this line is a common tangent to which both the centers or circles are lying on the same side. In this case, this is called a direct common tangent. Shortly, now onwards, I will call it as DCT. If you observe one more common tangent, to this common tangent, both the centers are lying on either side of the line, which is called a transverse common tangent. Shortly, we can write it as TCT. In this diagram, when D greater than R1 plus R2, we can see that we can draw two transverse common tangents and two direct common tangents. 2 DCT plus 2 TCT can be drawn in this case, case 1. If we analyze the second case, this is a direct common tangent, this is also direct common tangent, and this is a transverse common tangent. So in this case, we can draw two direct common tangents plus one transverse common tangent. Coming to this third case, here we can draw only two direct common tangents. We cannot draw any transverse common tangent to this particular case. Fourth one, at the point of contact, the common tangent drawn is the only direct common tangent we can draw. One direct common tangent, no transverse common tangents. In this case, as we can see comfortably that we cannot draw any common tangents to the circle, because the last case is coinciding case. Any tangent you draw anywhere, that becomes a direct common tangent to both the circles. So in that case, if you treat it as two different circles, two circles which are coinciding, everywhere at any point tangent drawn will become a direct common tangent to both of these circles. In that case, we can imagine that we can draw infinite common tangents, direct common tangents to the given two coinciding circles. So this is the way of getting number of common tangents, how many we can draw in each case, and we can categorize them also, how many direct common tangents we can draw, how many transverse common tangents we can draw. We can see like this, everything just based on the comparison values of D and R1 plus R2. Now let us see the properties of these common tangents can be drawn to the given two circles. As we have discussed earlier in 7 cases, in some of the cases only we could able to draw the common tangents. In that particular case, what are the properties of common tangents we are going to get? Let us see in detail. Now initially we see the case when D greater than R1 plus R2. Suppose this is the first circle with center A. This is the second circle with center B. Let us assume the distance between centers as D. Radius of the first circle taken as R1. Radius of the second circle is taken as R2. Suppose this is the common tangent, which is direct common tangent of the given two circles. If PQ is the direct common tangent, now how to find out the length of this direct common tangent? We see that part here. Here AB parallel to this, if we draw a line from Q which cuts the AP at N. Now clearly PQN is a right angle triangle here. This length of AP is R1 and length of QB is R2. Let us take this as R2. Then obviously AN also R2. Then this PN will be R1 minus R2. In this diagram, PQN triangle, we know QN length as T because these two are equal and this length is R1 minus R2. Now from Pythagoras theorem, we can calculate the length of PQ easily as hypotenuse D square minus R1 minus R2 whole square. So if two circles with radii R1, R2 are such that each circle is external to the other, we can draw two direct common tangents. Each one's length is under root D square minus R1 minus R2 whole square. We can show it very comfortably as shown just now. So here the length of direct common tangent equals to under root D square minus R1 minus R2 whole square. And one can prove very comfortably in similar way the length of transverse common tangent also. Similarly, the length of transverse common tangent we can prove it as D square minus R1 plus R2 whole square. These two lengths we can remember as standard results because every time deriving is not an easy task. That's why we can take them as some standard results. Now, along with properties of direct common tangents like their length, here I am discussing one more important point, that is about the points of intersection of the common tangents. If you observe this diagram carefully, in this diagram the circles are clearly, each one is external to the other. We are able to draw two direct common tangents and two transverse common tangents. We can see in the diagram very clearly that both the direct common tangents are intersecting at a point SE and internal tangent, this transversal common tangents are intersecting at a point which is taken as SI. We can see that this SI and SE are clearly collinear with the centers of the given two circles. We can draw one line passing through all these 4 points. We can show it with a simple geometry that these 4 points are always collinear. Now, these 2 points of intersection of common tangents, that is direct common tangents and transversal common tangents, together called as centers of similitude of the given two circles. When two direct common tangents are intersecting at this point, this is external to the centers, that is why that is called external center of similitude, and similarly this point is called the internal center of similitude. Here that is why we can notate them as simply SI. I stands for internal center of similitude and E for external. These two are external and internal centers of similitude which are collinear with AB. Because this point is dividing these two somewhere internally, now let us see in what ratio this internal center of similitude is dividing these two centers AB. For that, we take a simple construction here. If the point of contact is taken as some P, this point of contact is taken as some Q. Now, in the diagram, triangle APSI, QBSI, these two triangles are similar to each other because these two are right angles. Tangent drawn is perpendicular to the radius at that point of contact. That's why this is perpendicular and this is perpendicular, and we know that these two are vertically opposite angles are always equal. So, from A corollary, these two triangles are similar triangles. If the given two triangles are similar triangles, we know that corresponding sides are in proportion. Therefore, triangle ASIP is similar to triangle BSIQ, implies here ASI by SIB, these two sides ratio is equals to AP by QB. But AP is radius of this circle and QB is radius of this circle, which is nothing but R1 by R2. Therefore, center of similitude, internal center of similitude of given two circles dividing both the centers in the ratio R1 is to R2 internally. We can also show very comfortably that this external center of similitude also divides A and B in the same ratio R1 is to R2 but externally. That is why this SI and SE both are dividing AB in the same ratio internally, externally. We can recollect the word here harmonic conjugates. SI, SE both are dividing AB in the same ratio internally and externally. That is why these 2 points are harmonic conjugates to each other. Harmonic conjugates to each other with respect to the centers AB. So, we are comfortably shown that these 2 points are dividing the centers in the same ratio internally, externally, and hence they are called harmonic conjugates to each other. Now, coming to one more important point in this. Here, SISE, these two are centers of similitudes. We can construct a circle taking this as a diameter. We can construct a circle with centers of similitude as a diameter, which is defined as the circle of similitude. The circle with SI and SE as extremities of a diameter is defined as circle of similitude of the given two circles. We can also find one more important geometrical point, related to this circle of similitude, that at any point on this, the angles made by given two circles at this point will be always equal. Means from any point on this circumference of circle of similitude, if you draw pair of tangents to first circle as well as second circle, they are making equal angles. The angle between tangents drawn from any point on this circumference of circle of similitude to both the circles is always same. By using this particular definition point, we can get the circle of similitude in more comfortable way. If you are taking the circles as S and S dash, radii are R1, R2, here angle between tangents we know already as 2 tan inverse R by root S11 equals to second circle case we get 2 tan inverse first one radius if you take R1, second radius R2. Second circle equation I am considering as S dash. Then we are getting this condition. Eliminating 2 tan inverse both sides, squaring and simplifying. R1 square into S dash 11 equals to R2 square into S11. So locus of this point will be now R1 square into S dash equals to R2 square into S. First circle into second circle radius square equals to second circle into first circle radius square is the simple mathematical result we get for directly writing the equation of circle of similitude of the given two circles. This is the way of analyzing the points of intersection of the direct and transverse common tangents, which are defined as centers of similitude, and the circle drawn with centers of similitude as a diameter, which is defined as circle of similitude, and how to find out this circle of similitude by using this mathematical formula have been analyzed from this diagram very comfortably. And also we have proven that the centers of similitude are dividing always the centers in the same ratio internally and externally with R1 is to R2. Hence these two also can be taken as harmonic conjugates to each other with respect to the centers.